the weapon. Its casing made from a new magnesium alloy developed in Germany in 1908, dubbed Electron. Magnesium in its pure form is a tremendously light, shiny metal that rapidly corrodes. It isn't particularly strong, and when ignited, it is incredibly hard to put out. This highly reactive material burns so hot and aggressively that all three of these fire extinguishers can actually make fires worse. When sprayed with water, the burning magnesium rips the hydrogen and oxygen apart, providing an explosive atmosphere for itself. When sprayed with carbon dioxide, it rips the oxygen off carbon. Incredibly attractive as a fuel source in a bomb, but not as a structural casing. The Germans had formulated this alloy to address those problems. It was 9% by weight aluminium. They didn't fully understand why this made magnesium so much stronger, but this made the magnesium strong enough to be used in lightweight structural parts in planes and zeppelins of World War I. The war ended before this monstrous little bomb could be used for its intended targets, Paris and London. Just 1 kilogram in weight, thanks to its innovative casing, a single German bomber aircraft could carry hundreds of them. These tiny bombs were filled with thermite, which burned hot enough to ignite the magnesium metal casing. Similar bombs were used by the British when they attacked civilians in Dresden. When this bomb cracked through the roofs of the buildings below, it would ignite everything in sight. The goal? To overwhelm the enemy's city's fire departments. This horrible weapon of terror finally got its target during the Spanish Civil War when the Germans used it to lay waste to the Basque stronghold of Guernica, inspiring the great anti-war painting by Pablo Picasso, Guernica. And yet, for all of its terrible uses, today magnesium alloys have evolved, gradually being adapted and improved, being used in World War II aircraft engines and entering the commercial market with lightweight custom mag wheels but regenerative braking. Its battery, which Seth referred to as the Res, is just 1.9 kilowatt hours, 30 times less than even a low-range EV. This electric motor is designed for nothing more than harvesting kinetic energy in braking before a turn and unleashing it as a powerful low-end torque on the exit. This motor needs to earn every single gram it demands to make this energy harvesting system worth it, as every gram is being carried by the internal combustion engine at all other times. So, how did magnesium go from a material used almost exclusively for its reactivity to being an advanced structural material? Nearly 100 years of material science can help us answer that question. This is the material science of magnesium. This is the AZ91 magnesium alloy. It was the standard wartime high-strength magnesium alloy. You can tell what materials are alloyed with a metal by those letters and numbers in the name. Here, A is aluminium, making up 9% of the alloy's weight, and Z is zinc, making up 1%. These materials change the internal crystalline structure of metals to change their material properties in different ways. It's like really high-tech baking. These crystalline structures get extremely complicated, but we can think of it simply like trying to stack pool balls. Organizing 7 into the most compact arrangement will look something like this, forming a hexagonal outer perimeter. Now, when a second layer is introduced, it fills the little spaces between the balls, but there isn't enough space to fill every void. We could do this, or we could do this. Let's call them A and B layers. When we add a third layer, we have more options again. It can repeat the A layer, giving us a repeating AB-AB layering. This is the crystalline structure of pure magnesium, hexagonal close-packed, but a stacking pattern called a C layer, with a repeating ABC-ABC structure. This is face-centered cubic. Aluminium takes this structure. And while these stacking arrangements can seem like the result of pure chance, the actual impact on material properties is profound. These crystal structures wanted to form in the most compact direction, and face-centered cubic has more close-packed planes than hexagonal close-packed. Aluminium has 12 to magnesium's 3. But this doesn't make magnesium stronger, it makes it more brittle, and aluminium more ductile. Things get even more complicated as we add alloying metals. As the molten pool of metal cools, aluminium atoms can substitute themselves into the magnesium crystal lattice. But they are slightly smaller than the surrounding magnesium atoms, so they create tension in the structure and make it harder for atoms to slide past one another. These crystals grow in regions as the metal solidifies, but as magnesium cools, aluminium's solubility within it drops, so excess aluminium gets pushed to the edges of these growing crystals, until there is nowhere left to go and it is forced to create a new, complex intermetallic compound that is extremely hard as it has no slip planes, increasing the alloy stiffness. These are scanning electron microscope images of different magnesium alloys with varying percentages of aluminium. You can see that the ones with more aluminium have smaller crystal grains. That's because the magnesium hits saturation sooner and the boundaries grow sooner. Smaller grains make the material way stronger. This one here, AZ91, is the one used in those awful little bombs. But add too much and we just create a brittle material. It truly is high-tech baking. The percentages matter a lot. Zinc's primary purpose in the alloy is corrosion resistance. Pure magnesium is a nightmare when it comes to corrosion, which is surprising because one of magnesium's first commercial applications was alloy wheels, which are constantly coming in contact with contamination from the road and its own brake calipers. But the weight savings magnesium alloys provided were too tempting. Primary reasons, both related to inertia. The first is rolling inertia. We can calculate the difference in energy needed to spin two very different tires up to speed using this equation for rotational kinetic energy. The big industrial wheel requires 61,000 joules, while the sports wheel took just 2,400 joules. And it gets worse. Let's add in some bumps. Every time this wheel hits one of these bumps, it goes up, and we need to get it back down onto the ground as fast as possible. Every moment spent out of contact with the ground is a moment the engine isn't applying power. Gravity is too slow. We need a suspension. And the heavier the wheel, the more force the suspension needs to apply to push it back into contact with the ground. Removing unsprung weight is 4 times more effective than removing it anywhere else in the vehicle, which is why mag wheels, short for magnesium wheels, became a complete sensation in the 50s and 60s. So much so that some people call any custom wheels mags. Douglas was using magnesium in its wheels for the C-47 Skytrain, and that technology eventually made its way into the iconic mag wheels of the 50s. But magnesium wheels have one big problem: galvanic corrosion. Galvanic corrosion forces engineers to think about what materials are next to each other, like they are trying to stop 2 drunk uncles from sitting together at a wedding. This is the galvanic chart, and the further away 2 materials are from each other, the more important it is that they do not come in contact. Which is why the French must have been drinking wine when they designed the Statue of Liberty. This isn't even the original Statue of Liberty. The entire skin of the Statue of Liberty was made out of copper, while the skeleton was made out of puddled iron. Combined with salty Atlantic winds, the French essentially gifted America a giant battery. Galvanic corrosion happens when 2 materials that have dissimilar electric potentials are placed in contact with an electrolyte. This chart quantifies that, and here we can see that magnesium is the least noble thing on the chart and graphite is the most, an iron skeleton. Here, an electric potential has formed between the 2 materials that causes the 2 materials to trade electrons and ions. As they trade these ions, the anode material is gradually eaten away. This is exactly what happened to the Statue of Liberty because of Gustave Eiffel's design. A massive campaign was created to save the statue in 1986. The beautiful green patinaed copper skin would remain, but none of the original internal structure remains. Around 1,800 iron bars had to be carefully removed and replaced, but this time it would be replaced by stainless steel, much closer to copper on the galvanic series. Because of magnesium's place on the galvanic series, it needs a lot of extra attention to use safely. Take those magnesium alloy wheels. Every time the car brakes, corrosive particles of dust are shed on the rotor and strike the magnesium wheels. But that dust isn't just corrosive, it's often red hot, more than capable of burning through a thin paint or electroplated layers. After casting magnesium parts, they are often finished with a fascinating process called plasma electrolytic oxidation, where we use thousands of tiny little lightning bolts to turn the surface of the part into a ceramic. It looks amazing. We soak the magnesium in a bath of silicon and then apply a very high voltage. When the process begins, electrical arcs begin rippling across the material's surface, and each one drives current and heat down into the magnesium, allowing for the doping agents present in the bath to penetrate the part's surface, creating channels of hard ceramic. Magnesium is even finding applications inside the human body now. Magnesium is naturally metabolized by the body, so we can actually create magnesium alloy implants that slowly vanish. Medical implant screws frequently need painful secondary surgeries to remove them once the bones have healed. This is particularly difficult for children with fast-growing bones, so we can replace permanent titanium screws with magnesium screws that the body can break down over time. However, aluminium is a neurotoxin, so we can't alloy magnesium with that for biomedical applications. So instead, these screws use a special magnesium alloy called WE43, which contains a long list of rare earth metals like neodymium, yttrium, and zirconium. In 2013, Europe approved the first magnesium alloy screws and have been used in tens of thousands of surgeries, and the FDA approved them in 2023. Like many things in engineering,